Okay, welcome back everyone. So in this video, we'll be talking about operations on languages. So we've defined what a language is. It's a set of strings over a given alphabet. Now we want to see what kind of operations we can apply to languages. So we have the same operations that we can apply on sets. Some of the same operations that we apply on sets can be applied to languages. So the union, intersection, and difference are three of those operations. And so they're defined similarly as they are defined in set operations. So instead of redefining them, I'm just going to give a few examples. So I have the language L1, which is A, AB, AB, AB. And then the language L2, which is ABN for n greater or equal to 0. So what does this actually look like? Right, let's just write a few of the strings down. So I have AB0, AB1, AB2, and so on. And actually what that looks like is I have the empty string, right? Because any string to the 0 is the empty string. Then I have AB, then I have AB, AB, and so on. So this is my language L2, okay? So now what's the union of these two languages? Well, it's the language containing strings that are either from L1 or from L2, right? So I know that I'm going to have to include all the strings from L2, right, which is infinite. And to that, I'm going to have to only add A, right? Because A is the only string from L1 that isn't an L2, right? Because L2 actually contains AB and ABA, which is contained in L1. So when I do the union, the only thing I have to do is take this A and add it to this infinite language, L2, right? So then my union is going to be lambda, A, and then AB, AB2, AB3, and so on. Okay, what about the intersection? Well, the intersection is going to be the language containing strings that are common to both L1 and L2, right? So in that case, that's going to be, as I just pointed out, AB and AB square, AB and AB square. So those are the only two strings that are both in L1 and in L2. So then I have AB and AB square. Excellent. So now, what happens if I take L1 and I do different L2, right? So remember what this means. It means that I remove from L1 all the strings that are in L2. So if I remove from L1 all of the strings that are in L2, then I have to remove AB from L1 and AB2 from L1. So then all that I'm left with is the singleton language A, right? What about the other way, right? Well, the other way is it's similar, right? Instead of having L2, I have L2 minus the strings that are in L1, right? So then I have lambda, I skip these two guys, and then I continue with AB cube, AB4, and so on. So then that means that the language is going to be, well, let's write it a bit more compactly, right? It's going to be ABN, such that n is equal to 0, or n is greater or equal to 3. And that's the difference. Okay, so those are the classic set operations now applied to languages. Now there's some more language-specific operations. The first one is the reverse. So the reverse of a language, which is written L to the R, or just L of R, or the reverse of L, is defined as taking each string in L and then reversing it, okay? So what does that look like? For instance, for our same two languages from the previous example, It just means that, for instance, for L1, I take each of the strings and I reverse it. I reverse them. So I have A, then I do A reverse. I have AB, then I do AB reverse. And for AB, AB, I do AB, AB reverse. So what I get is, well, the reverse of A is just A, the reverse of AB is BA, the reverse of AB square is BA square, right? Okay, what about L2? Well, L2 requires maybe a bit more thinking. So L2 is AB, lambda, AB, AB square. Well, actually, let's not write it in the compact version. Let's write AB, B, then it's AB cubed, and so on, right? So then the reverse is going to be lambda reverse, AB reverse, AB, AB reverse, AB, AB, AB reverse, and so on, right? And what is that going to look like? Well, the reverse of lambda is lambda. The reverse of AB is BA. The reverse of AB square is BA square. Right now I'm going to write it compactly. The reverse of AB cube is BA cube, and so on, right? And so we can see that actually what happens is the string within the exponent, right? Again, I'm using this term exponent very loosely. The string within the exponent gets reversed, right? And so that gives me the language BAN for n greater or equal to 0. And that's the reverse of a language. Next is the concatenation. So the concatenation of two languages is defined as follows. So we're given two languages, L1, L2. Then the concatenation L1 concat L2 of these languages is defined as the language where you take each string W in L1 and concatenate it with each string in the language L2. So this is very much like the cross product of two sets, right? So you take, whereas in the cross products of two sets, you take the element in the first set and then combine it with every other element in the other set into a two tuple. You're just doing the same thing here, but doing a concatenation of each string in L1 with each string in L2. It's just that the order is important, right? So because you're doing L1, L2, this is all of the strings that look like a string from L1 and then a string from L2. A string from L1 concat a string from L2. So for instance here, if I have L1, which is defined in this case as the singleton language, just containing the string A, and L2 as AN for n greater or equal to 0. So in other words, L2 is, lambda, A, A2, A3, and so on. Then what is L1, L2? Well, it's the language A concat the language lambda, A, A2, and so on. And so what that looks like is you take A and then you concatenate it with lambda. You take A, you concatenate it with A. You take A, you concatenate it with A2. And so what that means is you take A, concatenate it with lambda, take A, concatenate it with A, take A, concatenate it with A2, and so on. And so then what you get is you get A, A2, A3, and so on. So actually the resulting language is really just AN, but for n greater or equal to 1. Okay. So I'll let you answer this question and this question on your own. I think they're interesting questions to practice. Okay, so that was language concatenation. the next operation is very similar to the exponential concatenation of strings. In this case, I just have the exponential concatenation, right? Again, this is very loosely written, exponential concatenation of languages. So what does that look like? That just looks like if I have a language L, then L to the N is just concatenating L with itself n times, right? So, for example, 1, I'm actually going to need a bit more space for this. So if I have L1 is A and Bn, right? So what does L1 look like? It looks like, well, A0, B0 is lambda, then A1, B1, so that's AB, then A2, B2, then A3, B3, and then so on, right? So this is L1. What is L1 squared? So it's, you take L1, and then you concatenate it with L1. So then, what does that look like? It looks like lambda, B, B2, B2, A3, B3, and then concatenate it with itself, right? Can I copy and paste? Copy, paste. Yes, I can. That's nice. Okay, that's nice. So again, what happens is I take each string in. Let me rename these languages, right? So let's say this is A and this is B. So then I take each string in A and then concatenate it with each string in B, right? So I take lambda, concatenate with lambda, with AB, A2, B2, A3, B3, and so on. Okay, so then that means that I first get lambda, AB, A2, B2, A3, B3, and so on, right? And then after that, I take AB, and then I concatenate it with every other string in, I take AB from A, and I concatenate it with every other string in B, right? So I take AB, concatenate it with lambda, with AB, with A2B2, with A3B3, and so on. So what does that look like? It looks like AB, lambda, so that's just AB. So actually we have a duplicate, which we'll just remove after. Then we have A, B, A2, B2, or sorry, no, we have, that's my bad. We have AB, and then AB, and then we have AB, and then A2, B2, and so on, right? And then the same thing for A2, B2. We have A2, B2 with lambda, A2, B2 with AB, A2, B2 with itself, and so on. And so in general, it looks like any string in this concatenation of languages is going to look like a IBI, a JBJ, right? Because it's going to be the same number of A's and B's for the first string with the same number of A's and B's for the second string, or like the second half of the string. So then that means that my language is actually going to be a NBN, a MBM for N, comma M greater or equal to 0, right? So that's what L1 squared would be. Okay, and lastly for this concatenation, what is this exponential concatenation? What is L to the 0? Well, L to the 0, we're actually going to always define that, and this is going to be for every L. So for every language, and in fact, for every L, so I'll just write every language. I'm going to say that L to the 0 is going to be defined as the set containing the empty string. And that's similar to the reason why taking a string and exponentiating it to the 0 is going to give you lambda. It's kind of the same reasoning here. It's just that here it's as if you take any string, you take all of the strings in L, and you just do W to the 0 to them, right? Then this is always going to give you lambda. And so the intuition is that if you always have lambda in your language, then it's just going to be the set containing lambda, right? Okay, but this is a very important like property to know about, because then you get surprising things like if you have the empty set and then you take the empty set to the 0, right? The empty set is a set, right? So it is a set of strings. It's the set of strings that does not contain any strings. So it's a language. And so you can apply this language operation to the empty set, but it'll actually give you, so if you take the empty set and you exponentiate it to 0, it'll give you the language containing lambda, right? Which is sometimes counterintuitive, but based on this convention, it makes sense. Okay, two more operations to go. So, given a language L, the star closure, also known as the clean star closure or clean closure, there's a bunch of permutations, but sometimes clean is in there, which is denoted by L star, is defined as the following. So it's the infinite union of the exponential concatenation of the language, starting at 0 all the way to infinity. So L star is L0, union L2, union L3, and so on. Okay, so in other words, if you want a more compact version, would be the infinite union from 0 to infinity of L to the I. This is the more compact version. Okay, so if I'm given the alphabet, okay, so this is going to be important. If I'm given the alphabet AB, what is a set, right? So I'm given a keyboard A, B. Now the question is asking me, what is a set of all possible strings over sigma? So in other words, what is a set of all possible strings that can be created with this keyboard, right? So I have A, I have B, right, and so on. So what are these strings, right? Well, I'm going to have strings of length 0, right? So because I want all possible strings, right? So one way of sort of counting these guys is saying, okay, I have strings of length 0, strings of length 2, strings of length 4, strings of length I, right? So strings of length 0, I just have 1, I have lambda. Then strings of length 1, I have 2, I have A and B, right? So remember what I'm doing. I'm trying to answer this question. What is the set of all possible strings? And so I'm just enumerating all these possible strings, starting with strings of length 0, now strings of length 1, next strings of length 2, so that's going to be AA, AB, BA, BA, and BP, and so on, right? And so strings of length 3, you know what, I won't write those. But what you should notice immediately, actually, is there seems to be a pattern or a mapping between this operation and what I'm writing down here, right? So if I sort of augment this string with a set operation, with like a set construction, then I have the set containing lambda. Next, I have the set containing AB. Next, I have the set containing all possible strings of length 2 over the alphabet AB, right? And so actually, this can also be written as sigma 0, right? And this is sigma 1, and this is sigma 2, and so on. So actually, the set of all possible strings over sigma is just going to be sigma star, right? It's going to be sigma star, which is the set of all possible strings of length 0 over sigma union the set of all possible strings of length 1 over sigma union the set of all possible strings of length 2 over sigma, and so on. Those are all the possible strings of any length over sigma. That's exactly going to be sigma star, right? And so that's why this is an important operation, because it allows you to 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 immediately produce all possible strings over an alphabet. And so actually then a language L, which is, remember what a language is. It's a set of strings over an alphabet sigma. So now actually a language L is just a subset of sigma star, right? So I guess a language over the alphabet sigma is just a subset of sigma star, okay? And so that's why sometimes people write down L, people sometimes write down formally. You're given a language L, which is a subset of sigma star. And maybe L is not the empty set, and so on. And then you keep on going, right? So that's why this, instead of just writing in natural language with what a language is, what L is, you can just use now a mathematical notation. You can use the subset notation to define what the language L is, right? So example 2, I'll skip just for the purposes of time, but I again think it's good practice. The last operation is not going to be very different from the previous one. It's going to be the positive closure of a language L. That's just the infinite union, but starting at 1. So it's the infinite union of the exponential concatenations of L starting at 1. So for instance here, given L4 is A and then AB, what is the shortest string in L4 plus? Well, L4 plus is L4 to the 1, union L4 to the 2, union L4 to the 3, and so on. So the shortest string, so if I write these guys down, I have A, B, and so on. The shortest string is clearly going to be A, right? Because this is the set this is the language that contains the strings that are concatenated with nothing else, right? So here, this A is going to be concatenated with at least another A. So then the smallest string here is going to be AA. And so then clearly as I keep exponentiating, I'm going to have longer and longer strings. And so the shortest string that I'm going to find is actually going to be in the first language here, which is going to be A. So then the shortest string here is going to be A. I'll leave this example again for you to practice, but this is again a very interesting example. I won't say anything else, but I think you should really carefully think about this as a true or false. Yeah, I'm not going to say anything else, but I recommend you try it. All right. So that's going to be it in terms of languages. So we first covered the definitions of strings, of alphabets, and of languages. Then we looked at string operations, and now we looked at language operations. Um, there, there may be exercises that you could um, look at to practice further. Those might be posted um, on my webpage. But in terms of content in the next videos, you're going to be introduced to your very first computational machines, your very first automata. So I hope you're just as excited as me because you're going to see that these are very cool, very interesting mathematical objects with which you can do a bunch of crazy stuff. Okay, well, until next time, stay safe, and I will see you soon.